I am using the 2009 version of MATLAB that you can download it from the university's portal. So this is how the workspace looks like. The first thing that you need to do is make sure that you assign the file path to the directory of your preference. You can do that by changing the path from over here. So I have it to the MATLAB video session. Now, on the right hand side, you can see that this space over here is the command window. This is where you put your commands. On the left, there is the current folder that shows the entries at the existing directory. And finally, it's the workspace, which outlines the saved values of your project. I'm gonna start with a very simple example over here. This is something really fundamental. You can assign to a variable, I'm gonna call it a value. As you can see, this entry appears now on the workspace. Okay, let's get started with the control stuff. The first thing that I'm gonna show you is how you can define a transfer function at MATLAB. To define a transfer function, we will use the tf command. The tf command accepts two arguments. The first one is the numerator of the transfer function, and the second one is the denominator. We proceed with an example. Assume that you would like to insert to MATLAB's command window the following transfer function. Now, this transfer function can be written in the following form. As you can see, I'm writing it in descending powers of the s variable. Now, I'm going to define two row arrays, which are the coefficients of the numerator and denominator respectively. The first one for the numerator is going to be 4, 2, and 1, and the second one for the denominator is going to be 1, 5, and 7. So if you would like to insert the transfer function h of s to MATLAB, what you're gonna need to do is use the command tf. So I'm going to define a transfer function object h, which is gonna be the transfer function of the numerator and the denominator. I am coming back to MATLAB's command window to show you how you can insert the object h, which is supposed to be a transfer function. So for our example, for our working example, we're having first argument is the row vector 4 to 1, and the second one is 1, 5 to 7. Now if you don't put a semicolon at the end of your command, you're gonna get in return what is the object that you just inserted to the command window. Now, as you can observe, at the left hand side of your workspace, we are having temporarily stored the object h, which is identified, its value is identified as a transfer function. We proceed with a second example. Assume the transfer function g of s 1 over s squared plus n plus 9. Again, we would like to insert this transfer function to the workspace of MATLAB. Now, as you can see, I only want to have one coefficient in the numerator that corresponds to the 0th power of s, and over here on my denominator the coefficient that corresponds to the first power of s is 0. So the arguments of the tf command can be written as the numerator can be just 1, which is essentially the same thing with having a 1 into brackets, and the denominator is 1. Just be careful, the second entry that corresponds to the first power of s is going to be 0, and the last one is gonna be 9. And again, you can obtain g by executing the transfer function command with the two arguments that we just defined. Coming back to MATLAB for the second example, I'm going to define the object, the transfer function object g, as using the tf command of the coefficients of numerator is just 1, while the coefficients of the denominator are the following. If I execute the tf command, this is what I'm gonna get in return. As you can see again on the left, we are having the object g, and the transfer function looks like the one that I wanted in the first place. Another way to define a transfer function to MATLAB's command window is using the zero pole gain model. What you're gonna need is the ZPK command. The ZPK command receives three arguments. The first one are the zeros of the transfer function in, again, an array form, the poles, again in an array form, and the gain. As a reminder, in the zero pole gain form of a transfer function, for example, g of s, the numerator and denominator are expressed as first order factors of the zeros and poles of the transfer function respectively. So for example, if we have m zeros and n poles, this is how the zero pole gain form is going to look like, where the zeros are z1 to zm and the poles are p1 to pm, and finally the gain k is going to be that. Now let's say that we would like to define a transfer function object. I'm gonna call it h1 of s to MATLAB, which has the following parameters. The gain is 2, the zeros are -3 and 4, and the pole is -5 and 6. So In order to define this object, I just have to use the zpk command, where first I'm going to insert the argument of the zeros, the argument of the poles, and finally the gain. What you end up having is the following transfer function I'm coming back to MATLAB to use the zpk command. Therefore, I'm going to define the transfer function object h1 using zpk, where for our running example we had for zeros -3 and 4, my poles were -5 and 6, and the gain was 2. If I do not insert a semicolon after executing the command, I'm gonna get in return how this object is gonna look like. So it is what we expected, and as you can see, now the transfer function object h1 in zero pole gain form has been stored to my workspace. With the transfer function objects, we can execute fundamental operations. So for example, let me define two transfer functions. The first one is gonna be C of S. So let me define first this transfer function, and a second one, G, being the following one. Now I can multiply the two transfer functions, and you can see the result. I can divide the two transfer functions and add or subtract. What you primarily need the transfer function operations is mainly to be able and derive the closed loop transfer function based on the open loop dynamics. So assume, for example, that you are having the standard architecture, the standard closed loop architecture with a unity feedback. Here is the compensator dynamics, the system dynamics, the unity feedback, and if this is the open loop transfer function, if you recall, the closed loop transfer function is given by this expression over here. Coming back to MATLAB, I'm gonna show you how you can define the closed loop transfer function if the open loop one is C of S times G of S. So over here we are gonna have C times G divided by 1 plus C times G. All of these are admissible properties of transfer functions. MATLAB conveniently provides a number of functions that plot the response of a system to the basic inputs, that is the step and impulse inputs. So let's start by defining first a boring first order system with transfer function G. Well, I can get the step response of this system and also through the impulse command, impulse with argument g, we can have its impulse response, as you can see. We can also obtain quickly the root locus plot of the system G using the command rlocus. And as you can see, we have the drawing where the pole of the open loop system is marked with an X. In general, in the root locus, what you're gonna get is the poles being X's and the zeros being O's or zeros. At this point, we are ready to use the main software modality for control systems analysis that it is available to MATLAB, and that is the SISO tool graphical user interface. At this point, just press SISO tool and run the command, and what you're gonna get after expanding the window is the control system designer GUI. Now the default there is a default layout of plots. I suggest that we remove them. You can customize the layout of the GUI by going to the View tab, and there are a number of different options over there. I'm just gonna leave them as is and gradually start filling the blocks, the view blocks, with the graphs that I'm interested in. So I'm gonna start by clicking the first partition and going to the tuning methods. I'm going to select the root locus editor. There's a number of options over here. It's gonna give you first of all the architecture of the control system, and there's a drop down box. Just use the default command, which is loop transfer C, not command, option, and press plot. Up to this point I haven't inserted any system into the software, so it's gonna be just a blank plot. As an example, I'm going to draw the root locus of a very simple system with one pole at -1 and another pole at the origin. I'm gonna start with a proportional controller. In the beginning, my C of S is gonna just be a proportional gain, and then I'm going to proceed by adding a PD controller and show you how we can change the architecture of the control system using the SISO tool. I will start by defining my transfer function at the command window and define the object to the transfer function object into the workspace. So the transfer function of interest is gonna be s square plus s, 1 over s square plus s, and it's gonna look like that. And now I'm gonna show you how you can import this transfer function into the SISO tool. For the time being, what I would like for you to notice is that I have already defined an object G, which is a transfer function at the workspace. To import my transfer function G into the SISO tool, first of all, you're gonna have to be at the control system tab, and then click on edit architecture and pick the first option, which is edit architecture, Let's click on that. Okay, so now what you're gonna end up having is a layout of the various blocks that are involved in a standard feedback control loop. So pretty much the idea here is to import from the workspace the transfer function into the corresponding block. Like for example, here I would like to modify the value of the system G. So what I'm gonna need to do is click this icon with the arrow here, and it gives me all of the available transfer functions at the workspace. The one that I have already defined is a transfer function G, the same name, and I'm gonna import this transfer function. Okay, so pretty much as you can see, this is the root locus of the second order system that I have defined. Recall that I'm having an open loop pole at 0 and -1, and based on our standard analysis, if you remember, we're gonna have two asymptotes, a breakaway point in the middle, and for any value of the gain k, we will not be able to change the imaginary part of the real part of the closed loop poles. At my control system designer, on the right hand side of the plots window, we're having a couple of space for a couple of plots available. So I'm gonna fill them up with the step response of the closed loop and the open loop system, such that we can compare them and see how our output will be from different values of the gain of the controller. So what I'm gonna do is that in the lower right space, I'm going to add the step response for the open loop system. The step response for the open loop system is this loop transfer option. Okay, so you can see that, well, I was supposed to have it below. Here you go. Okay, so as you can see, because of the pole at the origin, for one step input, the open loop response is going to be a ramp. Now you can see a description of the different type of responses on your left hand side. As you can see, this is the response, the loop transfer underscore C, and it's supposed to be the open loop transfer function. I'm going to add also the step response for the closed loop system. So in order to do that, I'm just going to click the available space for a plot. In the create new plot option, I'm gonna go to a new step. Okay, and now you're supposed to select the transfer function of which you're gonna draw the step response. Now you're gonna have to be careful over here and have a look at the input output mappings. What I want to do is obtain the closed loop transfer function. So I need to take the input being R and the output being I, according to the standard architecture of the control system designer. So we're gonna select the option transfer from R to Y, and let's plot it. Okay, what I want you to observe is that those red squares at the root locus are the poles of the closed loop system for a given k. So I can just modify, I can start changing the value of k. As you can see, by varying the values of k, we are getting our response, our step response of the closed loop system in the upper right corner is gonna change. So if I'm going to keep increasing the imaginary part, you can see that essentially I'm making my response faster, but at the same time I am adding overshoot to my system. Another comment that I have to make is that every time that you click the poles of the closed loop system, the red squares, well, at the lower part of the GUI, you're getting the current location of the pole that you have clicked or grabbed, and also it's dumping a natural frequency. If it's a second order system, these values are the actual ones. If it's a higher order system, the damping and the natural frequency is the approximation of a second order one. Okay, so in that case we're having a second order one, so this is going to be the damping and natural frequency for the current value of gain k. But you need to also remember that this is the control system that we are looking for right now. Pretty much we are just changing the value of the gain k, and for different values of the gain k, the root locus gives us the location of the poles of the closed loop system. If I'm going to right click on the plot of the step response for the closed loop system, there is a number of interesting options that MATLAB provides. The first one is the characteristics of the response. For example, I can identify where is the settling time, the peak response, the rise time, and its steady state value. Now if you click the blue dots, you can obtain their actual values. You can obtain a tag with their actual values. Like for example, here I just clicked the overshoot value, and it gives me the time of the peak amplitude and at the same time the overshoot percentage. If I come back to my root locus drawing and right click on the figure, I can get the design, I can insert into the drawing my design requirements. So if you go to the design requirements, there is a drop down selection here that you can choose and add your the requirements that are needed. Like for example, I can set a damping ratio zeta greater than 0.7, and it's gonna give me the shaded region which does not satisfy this requirement. And also I can add requirements, like for example over here what I'm gonna do is insert the natural frequency being at least 1 rad per second. As you can see, my controller, my compensator, does not satisfy the requirements for any value of the gain k. What is really nice is that you can also add design requirements in the time domain as well. So if you go to your step response plot, you can insert certain design requirements in the time domain. Like for example, for the step response bound, you can get different values. Like you can set it to be in 5 seconds, the settling time 10 seconds, overshoot 10%. And there are different options over here. If you press OK, so if you enter if your response is entering the shaded regions, it means that your output does not satisfy the design requirements. Like for example, in this case, you can see that the overshoot of my response exceeds the 10% value. Finally, if you would like to know the current value of your gain of the compensator, for which you're gonna get those the poles of the closed loop system, those red squares over here, what you need to do is right click on the root locus and go to the edit compensator option, and as you can see, this is gonna be the gain of your controller. Remember that this is the value of the gain k over here. What I'm gonna show you right now is how we're gonna edit our compensator, which is this block over here. This block over here is supposed to be the compensator, the controller. So how we're gonna change the compensator such that the design requirements that those arbitrary design requirements that we set are met. So pretty much what we're gonna do is that change the proportional controller with a proportional derivative one. So the way that we're gonna do that is that so the proportional derivative controller has the following form. There's gonna be a gain, and we are adding a real zero to the open loop transfer function. So now my compensator looks like that, and then I'm gonna have to tune my gain. Okay, so now what I'm gonna show you is how we can enter this transfer function of the compensator to the root locus. So what you need to do is right click on, you cannot even right click, you can just do it from here. So if you go to the upper left corner of the root locus editor, as you can see there are a bunch of selections of pole and zeros that you can add to your root locus. The first one is option is adding a real pole, the second one adding a real zero, and then we're having the addition of a pair of complex poles and a pair of complex zeros. In our case, remember that we would like to add a real zero. This is the PD controller, so I'm just gonna click this O and then select and then place the zero to the real axis. This is a pattern that you are already familiarized with. I placed the zero to the left of my fastest pole of the open loop transfer function, and I'm getting this split over here, which where my poles break away and break in. One converges to the zero and the other one to infinity. So now what I can do is I can tune the gain in order to bring my poles to the desired locations. Let me play a little bit around with this. So I can just manually tune the root locus such that I can bring where the poles of the closed loop transfer function where I want. So this is just an example of how you can edit your compensator. Now if you right click on the root locus and you go to the edit compensator, you can see the addition of the real zero. So the location of the real zero is going to appear to the edit selecting dynamics region. MATLAB as a convention for the compensator that I added. So when I added this real zero, the convention that it uses is written like that. However, my convention, if you remember, the one that we use is like this. So if you would like to get this gain over here, so this is what MATLAB uses. So if you would like to get this gain over here, you're gonna have to do an extra step. So the only thing that you have to do is drag tau outside, okay, and 1 over tau is supposed to be the location of the zero that you added. So just be careful about that. and if you want to get this k over here, you just have to do this conversion, which is not particularly difficult. Okay, let's do a final design example. The idea here is assume the open loop transfer function. So consider this system over here. We would like to design a lead compensator such that the closed loop system has the following specification. Overshoot is less than 20% and the rise time is less than 0.3 seconds. The architecture of the system that we would like to design has this form over here. So this is how the block diagram is going to look like. Design requirements translate into the following numbers. The overshoot, an overshoot less than 20% results to a greater zeta from 0.5, and the rise time less than 0.3 seconds results to a natural frequency which is greater than 6 rad per second. So I'm gonna go now to my control system designer. On the left I'm having the root locus, and on the right the step response of the closed loop system. In the root locus I'm gonna enter the design requirements for the problem at hand. So I'm having a damping ratio that's supposed to be greater than 0.7, and at the same time we also had a requirement for the natural frequency. This is 6. Okay, so here are the design requirements, and I'm gonna go to my step response and insert the characteristics of interest. The first one was the rise time. As we can see, we're having a value of 0.39 for this value, and the other one is the peak response, where I'm interested for the overshoot. Now, in order to decrease the rise time and bring it below 0.3, I have to increase the gain k, while my system becomes faster. As you can see, the result is that my overshoot is increasing. Therefore, the proportional controller is not going to suffice if we want to achieve the design specifications. So what I'm gonna do is that I'm gonna go to the root locus editor and add a lead controller. So first I'm gonna place a 0, and we're also gonna add a pole. So let me go and edit by right clicking on the root locus editor. I'm gonna go to the edit compensator, and I'm going to edit the position of the 0 and the pole. So I'm gonna bring my 0 to -2, and then my pole is gonna be further from the 0. In this case I'm gonna bring it to the location -13. So this is how now my root locus is gonna look like. I'm just gonna modify the value of k such that I dislocate the poles. As you can see, bringing the dominant pole, those complex conjugate poles, in outside of the shaded regions of my specifications. As you can see, I'm having a rise time which is less than 0.3 and an overshoot that's less than 20%. Therefore, we have accomplished the design requirements.